This is George Koutouris from Audion, and today I'm glad to present our recent work on audio effects for multi-source oralizations. Very briefly, oralization is the process of simulating how a given signal sounds in a virtual space. It offers a subjective approach to assessing simulation results, in contrast to the objective approach through room acoustic parameters such as reverberation time or sound pressure level. To create a similar oralization for Herphone reproduction, the binaural impulse response between a source and a receiver is convolved with an anechoic signal that is a signal without any reflections recorded. It sounds like this. The result is an audio file that recreates how the listener would hear the input signal from the source inside the room. There are situations where more than one sources are involved in the oralization. Imagine a cafeteria with several people speaking at the same time, musicians playing in the background, and noise from cutlery taking place. This is a so-called soundscape. For a realistic simulation, all these different sounds should come from different sources in the room model and should be assigned separate anechoic files. Still, only one receiver location is used to gather the convolution from all sources and their anechoic files, which are finally mixed in a single output. We can see so far that such a multi-source oralization requires a large number of anechoic files, and it can be difficult to obtain all of them. A solution to this is to use fewer original anechoic files and make variations of them to assign to the different sources. Obviously, this method cannot be applied to any scenario, but it can prove to be useful for applications where we have similar sound sources, such as orchestras or crowds. In this paper, we introduce an effective workflow in Audion for creating random variations of single anechoic files and applying them into multi-source oralizations. A chain of audio effects is employed to transform the various properties of the original files. Such properties can be pitch and speed, spectrum, and duration. The key point here is the effect parameters are varied randomly, which makes the process fast and unbiased. Okay, let's see that workflow in detail. One or more input signals are processed by the chain of audio effects, which assume it's a black box for now. The chain produces a number of variations which are assigned to an equal number of sources and are convolved with the corresponding room impulse response. This gives a set of convolutions which are then mixed together into a single output file. This workflow can be expanded for more input signals. Now, if we open the chain of audio effects box, we see that it consists of several effects chosen by the user, and each effect is controlled by a number of parameters which vary randomly within some user-defined limits. In this study, we use 5 of the effects which are available right now in Audion, and these are the change duration, phase vocoder, chorus, spectrumizer, and amplitude modulation. The change duration is used to alter the overall length of the signal, not by changing the speed, but by using random repetitions, cuts, and silences. The phase vocoder is pretty known in the literature. It works in the frequency domain by applying an FFT on time segments of the input signal. By modifying the amplitude and the phase of each spectrum component, we manage to change the pitch and speed of a signal independently. This is very important because we can, for example, increase the pitch of speech without making it faster, as it would happen when resembling in time domain. The chorus effect in Audion tries to mimic the variations of musicians that perform the same piece, for example, a string group. However, it doesn't apply only to musical instruments, but vocals as well. The variations between the musicians are mainly pitch and time. An effective way to include both attributes in one is to construct a continuous changing delay line as a function of time, which varies randomly within a specified interval. This is then translated into continuous changes of pitch and speed by resampling. The spectrumizer effect makes random changes to the spectrum of the input similar to an equalization filter. And in this way we attempt to alter the color of the signal, for example the texture of a violin. In contrast to the rest effects, the parameters of this one do not change over time. Finally, the amplitude modulation effect uses a random gain envelope as a function of time, defined between a minimum and a maximum percentage change. The envelope is then applied on the amplitude of the input signal. The period between the changes in the amplitude depends on the application. For example, the loudness of speech in a restaurant may vary quite slowly, that is every 10 to 20 seconds. Let's see how we can apply a set of effects and the multi-source oralization workflow in two application cases, a string orchestra and crowd in a cafeteria. We will play some audio examples which will be most accurate over headphones. For the first case, we try to convert a string quartet into a full string orchestra. If we mix all four anechoic signals from the instruments, it sounds like this. Each of the input signals is processed by the chorus, spectrumizer, and amplitude modulation effects. This chain creates variations assigned to independent sources in an Odeon model of the Concertgebouw concert hall in Amsterdam. Initially, we created 12 variations for each instrument, and then we followed a typical orchestra arrangement which uses different number of instruments and offers better frequency balance. First, let's listen to the quartet alone as it sounds in the middle of the stage. Now, let's listen to case 2 of the full orchestra. The overall impression from this example is that we can achieve realistic variations of pitch and time for each file. The full orchestra oralization gives the impression of an ensemble of strings. However, several attributes of the music performance are still not included in our effects, for example vibrato, which is different for each musician. Also, the recordings were performed by amateur musicians, which means that mistakes in pitch and timing can be exaggerated when making several variations of them. A final important remark is that single microphones have been used, which do not capture the full directivity of the instrument. A better approach that has been suggested is to use multiple microphones around. For the second application, we create a crowd of 30 sources inside the cafeteria. We use two different anechoic speech files to generate 15 variations for each. The first file is a male speech in English.
There are different types of decibels, which are relative to a different reference. This reference is very important.
While the second one is a female speech in Brazilian Portuguese.
Não te deixes destruir, ajuntando novas pedras e construindo novos poemas.
Both files are processed using the phase vocoder change duration, and amplitude modulation effects. Here we see the distribution of the 30 sources in an audio model of the cafeteria. On top of them, we place an extra source which is assigned a different anechoic file and serves as a speech in focus for a receiver next to it.
So off went the emperor in procession under his splendid canopy. Everyone in the street and the windows said, "Oh, how fine are the emperor's new clothes!"
We will hear an example when the speech in focus is placed on the left of the receiver.
So off went the emperor in procession under his splendid canopy. Everyone in the street and the windows said, "Oh, how fine are the emperor's new clothes! Don't they fit him to perfection?"
The example shows that the chain of fused effects introduces sufficient variation for a crowd oralization. One of the problems is that we can identify repetitions of the input speech files for the sources closer to the receiver. Variations sound still within a given gender, and some of them also sound artificial when listening separately. However, the final mixed result is quite convincing. With our proposed workflow, complex multi-source oralizations are possible. This is facilitated by creating large populations of anechoic files from a few input signals through an automatic process that provides fast, unbiased, and realistic results. Currently, we choose the effect parameters manually and subjectively. However, for future work, the parameters could be derived by listening experiments or other objective methods. Finally, we could include more effects in our list, such as vibrato for strings or moving sound sources for a crowd simulation. Thank you.